In this video, we're going to be examining the graphs of logarithms and their properties. In problem 1, we're asked to state the domain and range of the function where f of x is equal to the natural log of 1/3 minus x. Remember that since this is in logarithmic form, the f of x represents the power. F of x is the power because it is equal to the natural log. We have f of x equal to the natural log of 1/3 minus x. Since we have the natural log of 1/3 minus x, we're now free to consider what effect this has on the graph. Remember that the different parts have different values. The power can be any number at all, any real number. It can be positive, it can be negative, it can be a fraction, it can be anything, including 0. The base has to be a positive number greater than 0, and it cannot be equal to 1. The answer part, in contrast, also, because of the base being strictly positive, the answer part has to be strictly positive, but it can be 1. These are the restrictions that we have on the different pieces in a logarithmic equation. Now let's look at what we have here. We have 1/3 minus x. When we're looking at 1/3 minus x, this means that this is the answer part since it is sitting next to the natural log. It must be strictly positive, which means that we can take the 1/3 minus x and set it greater than 0. Then we can solve the inequality by moving the 1/3 to the other side. This gives us negative x is greater than 1/3, or negative 1/3. When we multiply both sides by a negative, this will give us that positive x is less than a positive 1/3. Remember that in order to change the inequality, when you divide or multiply by a negative, you have to reverse the symbol around. This tells us that x can be less than 1/3. Our domain, then, are all the values that are less than 1/3. This would be negative infinity up to 1/3, but it cannot equal 1/3, or this will be 0, and our answer part must be strictly positive. The range of most natural logs is going to be from negative infinity to infinity, and that will be the same here. It goes forever in both directions. Remember about what the graph of a typical one looks like, which is like this. This one, however, has been reflected across the y-axis because we have a negative on the x. It's also been shifted a little bit. We could think about this one instead as representing a negative times an x minus a 1/3. This means that the graph has been shifted to the right by 1/3 and reflected across the y-axis. The actual shape of this graph then has to be a little bit to the left of 1 and coming up like this. Let's now look at the next problem. Here's a better picture from Desmos that shows you what the graph looks like. And note that it does go below the origin. In my previous picture, I accidentally had it going above, so I've fixed it for you here. Now let's take a look at the next problem. State the domain and range of the function. While we're looking at the domain and range of this function, we need to figure out what it's going to look like. In this case, we want to state the domain and range of the function f of x equal natural log of quantity 5 minus 2x, close the quantity, minus 4. The minus 4 is not a part of the natural log. It is just fine and might even be a better way of writing it to put negative 4 plus the natural log of 5 minus 2x. Then you will make no mistake and include the negative 4 as part of the argument to natural log. And that is what we call it, an argument to the natural log function. We want the domain, which is, in this case, going to be affected by the answer part. Remember that here, our base is e, the function itself is the power, and then our answer part is going to be a part of what we're looking for with the domain, the answer part of 5 minus 2x. Since we have 5 minus 2x, what we need to then look for the next part is simply what are the restrictions on 5 minus 2x. The answer part has to be greater than or equal to 0, so 5 minus 2x has to be greater than 0, not equal. My bad for saying or equal. It's such a habit. So we're going to add 2x to both sides, and that brings us to the equation 5 is greater than 2x. Then I'll divide both sides by a positive 2, and because I'm dividing by a positive 2, I don't turn the symbol around. This tells me that 5 halves is greater than x, which is the same thing as saying that x is smaller than 5 halves. Notice that the narrow end of the symbol points towards the x in both cases. This means that my domain is going to be on the little end to the left, negative infinity up to 5 halves and stop. Don't include 5 halves because the answer part cannot be 0. Now we need the range. Again, this is basically one that has been shifted in several different places. Now shifting is not going to affect the domain. The domain is affected only by the answer part. In this one, we have a minus 4, which will move the entire graph down 4. Will that change what it looks like? Yes, it'll change what the graph looks like, but will it change the domain? The answer to that is no. It will also not change the range because the graph does go up forever, though very, very slowly, and it does go down forever very rapidly. So in this case, the range is again from negative infinity to infinity. Let's take a moment and graph it on Desmos to see what it really looks like. In this case, we can see that it has also been reflected across the y-axis. How does that come about? Again, you can write the problem as negative 4 plus the natural log, factor the negative 2 off of the x and the 5, and that will give you negative 2 times x minus 5 halves. Note that you have to divide the 5 by the 2 as well. This means that it's been shifted to the right by 5 halves, moving this way, and that it's been reflected across the y-axis this way, and that it's been stretched vertically by a factor of 2. We can see that our range of negative infinity to infinity is still accurate, though it is still a very slowly climbing function, climbing to the left. Let's now take a look at the next problem. State the domain and vertical asymptote of this function. This function is log of 3x minus 5. We're to find the domain and the vertical asymptote. Let's think about what we've done in the previous problems and see if we can rewrite the equation in a more correct form. This would look like the log of 3 times x minus 5/3. What's happened to our graph? This tells me it's been shifted to the right by 5/3. This tells me that it's been stretched or compressed in the horizontal direction. This is a horizontal stretch compression. Now, when I'm looking at this, I know it's gone to the right by 5/3. So what is that going to do to the picture? Don't forget that in this case, the variable term was positive, which means that it still has the basic shape that we associate it with logarithm, which is like that. But because it's gone to the right by 5/3, instead of crossing at 1, it's going to cross at 1 plus 5/3, or 3/3 plus 5/3, which is 8/3. 8/3 is just short of 3. So we should have the graph coming up like this, and it should be stretched a little bit, but not in the vertical direction, in the horizontal direction instead. So our basic shape is the same, but going off this way. What has happened to our domain? In this case, our domain is going to be starting at 5/3. And let me draw a better picture. I'm really kind of challenged on these. Since everything's been shifted to the right 5/3, that means that this line where it's 0 is also shifted to the right by 5/3, which is 1 2/3, which means that we have an asymptote at 1 2/3, and then it comes up and it crosses here as it normally does. So the vertical asymptote then must be at 5/3, or x equal 5/3. Let's take a look at what it would look like on Desmos after we write down the domain. The domain is going to start at 5/3, which is 1 2/3, and go to infinity. Does it use 5/3? No, it does not, because it's a vertical asymptote, and that means it can't be there. Thus, we have it starting at 5/3 and going off to infinity. This is our domain. Now let's take a minute to go graph it on Desmos and verify our suspicions. Here's the true graph on Desmos. Notice the horizontal stretch, which is pulling it sideways and making it go up even slower than it already normally does. Let's take a look now at the next problem. State the domain and vertical asymptote with the function f of x equal negative natural log of 5x minus 5 plus 3. Again, we're going to take the problem and we're going to put it in a better form. Notice that the negative at the front is going to reflect it across the x-axis. So we'll graph two of these in order to see what's going on. Let's first start with the first picture. We have negative the natural log, and now we're going to rewrite by factoring off the 5, and that will leave us with x minus 1 inside the parentheses. Then we have a plus 3, which I could move to the front and make it 3 minus that natural log. The 3 is going to shift the whole picture up. When I'm looking at the picture, it will go up 3. The up 3 will give us a vertical shift. This in here is going to give us a horizontal stretch by a factor of 5. And we've got a shift to the right by plus 1. Now let's take a look at the picture and see what's happened. Don't forget that the negative is going to reflect it across the x-axis. Let's take a minute and sketch out a quick picture, and then we'll use Desmos to get a more exact one. Let's look at what it would look like before we shift it up 3 and before we reflect. I'm going to take the picture to the right 1 so that my asymptote is shifted now over here, right 1, and that means that it will cross at 2. But because it's being stretched, it's going to go up slower than normal because it's being pulled to the side. Now what I have to do is I have to reflect it across the axis and shift it up 3. To reflect across the axis, I'm basically going to be coming down like this and then reflecting here. That reflects it. The next thing I want to do is shift the whole thing up 3. So if I shift the whole thing up 3, it's almost like it's coming down something like this. Let's now go graph it in Desmos and see if we're correct. You can see from the picture that I didn't get mine coming down fast enough. So let me fix that now. It should be coming down a little faster, and that means that it's going to cross out here somewhere and come down. And I didn't have it coming down fast enough. You can tell that the basic shape is the same. The range is going to be all real numbers since it goes down forever and up forever. The domain, however, has been shifted. It is approaching the value of 1 as a vertical asymptote, and that will make our vertical asymptote x equal 1, and our domain will start at 1 but not include 1 and go to positive infinity. Let's now take a look at the next problem, which is number 5. State the domain, the vertical asymptote, and the end behavior of the function. End behavior is what the function does as it goes to the right. Does it go up forever towards positive infinity, down forever towards negative infinity, or does it approach some value as a horizontal asymptote? Natural log and logarithm functions do not approach horizontal asymptotes. As it goes to the right, it will either approach infinity or negative infinity. That will be our end behavior. Let's now look at the log base 3 of x minus 1. This has been shifted to the right 1, which means that instead of having the y-axis as the vertical asymptote, we have the line x equal 1 as the vertical asymptote. Since our base is 3, we can assume that it has basically the same shape it normally does, but instead of approaching the y-axis as it's coming up, it's going to be approaching that line at x equal 1. Then it crosses through the x-axis there at x equal 2, and then it will keep going up. This is basically what it looks like. As x approaches 1 from the positive side, where is it going? As it's getting close to 1 from the positive, that means approach from the right and keep following the curve coming down. That means it's going towards negative infinity as it approaches 1 from the right. As x goes to positive infinity off to the right, the function does approach positive infinity. Let's now take a look at the next value that we have. Oh, and we did forget to give the domain. That should be open 1 to positive infinity. Let's now move on to problem number 6. In problem number 6, we are asked to find the x-intercept of the function. We're looking for the x-intercept of the function f of x equal log base 2 of 2x plus 4, the quantity, minus 2. Remember that we can always move the negative 2 to the front so we don't make the mistake of thinking it's part of the logarithm expression, which it is not. The base is 2. The answer part is 2x plus 4. The negative 2 is a part of the overall expression, but not part of the logarithm expression. When do x-intercepts occur? Well, remember that this has the effect of moving the entire graph down 2. We will need to factor the 2 off of this, and that will give us a 2 times the quantity, x plus 2. Remember that you can think of x plus 2 as a double negative, which means that it's actually moved to the left 2. And it's being stretched horizontally by a factor of 2. So we have a normal logarithm which looks more or less like this. We have shifted it down 2 and left 2. So we're going to take this spot right here, which is normally at 1, 0, and we're going to shift it down 2 and to the left 2. So it comes down 1, down 2, and to the left 1, 2. That point went to right there, which means that our graph should be looking like this and growing very slowly. Since it shifted to the left 2, since this value right here is negative 1, that means that it is approaching the value of negative 2 as an asymptote. What would the x-intercept be? Well, the x-intercept occurs when y is equal to 0. The y value is the function value here. So what we need to solve is the problem log base 2 of 2x plus 4 minus 2, or with a negative 2 plus the log at the front, equal to 0. I can move the plus 2 to the other side, and that will give me the next equation, which is log base 2 of 2x plus 4, which is equal to 2. Now that I have it isolated in logarithmic form, I want to switch to exponential form. the base is 2, the power is 2, and it equals the answer 2x plus 4. What number is 2 to the second power? That's 4. So I have 4 equals 2x plus 4. When I subtract 4 from both sides, this tells me that 2x has to be equal to 0, which means that x has to be equal to 0. Note that this does not mean that the answer part is 0. Just because x is 0 doesn't mean the answer part is. And in fact, it's not. It's 4. This makes sense because 2 squared is 4, and when I get the 0 plugged in, I get 4 for the answer. Therefore, my x-intercept, where it crosses the x-axis, is going to be where y is equal to 0 and x is equal to 0 as well. So my graph is a little off. It should be coming up a little bit higher. Let's take another look and let's graph it a little bit more accurately. It's going to be coming up something like this. Now let's take a look at Desmos and see what Desmos looks like. Here's the graph that is done on Desmos. You can see it definitely is crossing the x-axis at the origin, and you can see that it is approaching the value of x equal -2 as a vertical asymptote. Let's now look at the next problem, which is number 7. In this problem, we wish to match each function in the figure below with the letter corresponding to its graph. When we look at these, we can imagine, if we will, that the g of x's are replaced with y's. So for example, for the first one, I can think of it as y equals the log base 2 of x. This means that I have 2 to the y power equal to the answer part x. When I think about this, this means that if I have a y value of 1, then I should end up with an x value of 2. So I'm looking for a graph where the y value would be 1, but the x value would be 2. The only graph that could possibly be is number A. This one must be A. What about the next one? If I rewrite this one would have the form that 5 to the y power is equal to x. This means that when y is 1, the x value will be 5. I don't have 5 out here, but I know that it's got to be pretty low, and it's definitely not this one, because this has a y value of 1 when x is 3. I'm guessing it is C, D, or E, but I'm not sure which one yet. Let's take a look at the next one. The next one says 25 to the y equals x. This should be stretched more in the horizontal direction, because this means that when y is 1, the x value is way out there at 25. It looks to me like this one must probably be E. If that one is E, then this one has got to be either C or D. Let's see if we can compute which it is. When we look at the next one, this one does no base written, but it's log, so the base must be 10. 10 to the y is equal to x. Which of these would be stretched more in the horizontal direction? I think 10 to the y would be stretched more, so this one must be D. That makes this one be the one remaining long one, which is C. Let's see if this works for this one. This is natural log because there's no base written, but it has ln. That means e to the y power is equal to x, which must mean that when y is 1, my x value is e. Remember, e is very close to 3. And on this graph right here on the orange, you can see that when y is 1, it is very close to 3. In fact, it looks like it's at 2.7, which is E, or about E. That makes this one choice B. Let's move on to the next problem. Before we do that, though, let's notice what happened. The ones with a smaller base go up faster. The ones with a larger base are stretched in the horizontal direction and go up more slowly, but when they approach down here, they go more rapidly. Let's now look at the next problem. Match each function in the figure below with the letter corresponding to its graph. We have a normal looking natural log, which is A. We have one that is coming down, which is B, which looks like it might have gotten reflected, except that it didn't. Instead, it's got a fractional base. This one also has a fractional base. Let's see if we can use the strategy we used last time to figure out which one this is. This would be 3/4 raised to the y power equal to x. This means that if y is 1, x should be 3/4. The y equal 1 line is right here. When we look at this line where y equal 1, which one appears to be about at 3/4? To me, it probably is the blue one. And because the blue one is coming down in the wrong direction, I know that that's probably the correct one. Let's look at the log of 1/3, base 1/3 of x. This means that 1/3 raised to the y power is equal to x. When y is 1, x should equal 1/3. This says when y is 1, x should be 1/3. Well, x is 1/3 would be higher up. Uh-oh, maybe we got it backwards. Let's back up and try it again. Did we get it backwards? Looking at this one, let's see if we've got the right one. It looks to me like 3/4 might be closer to the green. So perhaps this one should have been C, and that will give me this blue one to be the 1/3. To be honest, I think the picture is a little misleading. It's a little off. Maybe if we made the picture larger, it would make more sense and look a little clearer. If this is C and this is B, that leaves the one in the middle to be A. Does that make sense based on the graph? Yes, this is a normal logarithm with a normal base that's greater than 1. Remember that when you're doing these, you need to check and double check your answers. I've blown it up just a little bit so that you can see that that probably is the correct way to have it. Let's now look at number 9. In number 9, we wish to do the same thing, match each function in the figure below with the letter corresponding to its graph. In this particular problem, remember that we can always factor out the negative, and then that will take it out off of the +2 as well, so that we have a double negative there, giving us back the positive. This is the log base 4 of a negative applied to an x minus 2. This means it actually went to the right by 2, but it got reflected over the y-axis. If it got reflected over the y-axis, then it does not have the normal shape where it comes up, but instead goes the other way, something like that. That's what the B graph looks like. However, this one should have been shifted to the right 2. Did it get shifted to the right 2? Normally, it would be crossing at 0, 1. The blue graph is still crossing, not 0, 1, 1, 0. The blue graph is still crossing at 1, 0, so it has not been shifted. That means we need to look for another one that looks like it's been shifted. Since we are reflecting across the y-axis, remember that it may have a slightly different look than what you're used to seeing. Let's sketch a quick graph of what it would look like if it had not been reflected so that we can understand what's going on. In this case, it would have been shifted to the right 2, which would have moved everything over so that it would have looked like this, more or less, crossing through here. Now, if we reflected this, what we would have was this would now cross over here at -3, and it would be coming up like this. Now we take this picture and we shift it to the right 2, and now we've got it. This looks like the correct one. If we shift that one to the right 2 after we've reflected it, then we should have part B. Let's take a look at the next problem. In the next one, we can see that we have a negative at the front, which means it's been reflected across the x-axis. So instead of opening the way it would normally open like this, it's going to instead come down and have some kind of behavior that looks something like that. However, this one's also been shifted. It's been shifted by a -2, which means it went left 2. Which of these might look like this, but shifted to the left? That looks like C, the green graph. Thus far, we have B and then C, which leaves the last one to be A. Let's verify that that is what it looks like. This would give us a double negative, which would again mean that it's gone to the left 2. But it's a normal graph, and it has no negative at the front and no negative on the x. So it's just been shifted left 2. So instead of crossing at 1, 0, it crosses at -1, 0. That is definitely A. Let's now go on to the next problem, which is number 10. Number 10, we are to use a graphing calculator to find an approximate solution to the equation, round to 3 decimal places. Here is our problem. We have log of 2x minus 3 plus 3 equal negative log of quantity 2x minus 3 plus 4. Do you see that we have two terms that have the log of 2x minus 3 in them? We can add this log to the other side to combine our like terms of log of quantity 2x minus 3. When we add them to both sides, this gives us 2 of the logs with a 2x minus 3 on it. Then we have the plus 3 equals a 4. Our next step would be to get the constants together by subtracting the 3 from both sides, which will give me now the equation that 2 log of 2x minus 3 is equal to 1. The next thing that you want to consider doing is either dividing both sides by the 2 or pulling the 2 in as a power on top of the answer part. It can be done either way. If we think about dividing both sides by 2, this will give me the log of 2x minus 3 equal to 1/2. Now I need to switch and use exponential form. It's log, so the base is 10. It's being raised to the 1/2 power, which is a square root, and it equals 2x minus 3. I'm going to write this as the square root of 10 and then add the 3 to both sides of the equation. When I add the 3, that will move the 3 to the left, but I can't combine the square root of 10 and 3 since this is irrational and this one is rational. This is now equal to 2x. Then I can divide both sides by the 2, and this gives me x is equal to the square root of 10 plus 3, all divided by 2. You'll need your graphing calculator or your scientific calculator to figure out the rest of it. Turn it on and then enter the square root of 10. Once you have the square root of 10, hit equals, and then add 3 to it and hit equals again. Now take that combined sum and enter divided by 2 and equals. You will have an approximate decimal number of about 3.081. That's rounded to the third decimal place. Let's take a look at the last problem we have in this homework set. What is the domain of the function natural log of x minus 4 divided by x plus 1? When we're looking at this particular problem, remember that this is all part of the answer part. The x minus 4 divided by x plus 1 is the answer part, which must be greater than 0. That means that x minus 4 divided by x plus 1 has to be strictly greater than 0. I need to consider what we did in the previous section and find out where this is going to be 0. To do that, I can think about the two lines, x minus 4, which is going to be 0 whenever I hit x equal 4. So this means that as long as I am over here above the value of 4, it will be strictly positive. What about the x plus 1? The x plus 1 becomes 0 at the value where it is -1. This means that when I'm looking at this particular graph, it's crossing at -1. It's going to be positive whenever I get to the other side, and I drew it on the wrong side, my bad. X equal -1, which would be over here, which would put it here. As long as x is to the right of -1, it's positive, and to the left, it's negative. This means if we look at the number line, that I've got possibilities here of where they're positives and where they're negatives. My two numbers I need to think about are -1 and 4. I know that the first numerator is going to be positive when I'm out here, and it's going to be negative when I'm on the other side. Let's look at the other line. The other line is going to be positive, provided I'm to the right of +1, and it's going to be negative on the other side. If we look at these two lines, in order for the whole thing to be positive, I need to be where they're both negative or both positive. I have to be above 4 for them to both be positive, so that would tell me to go from 4 to infinity. On the other hand, where are they both negative? Well, I can't allow x to be a -1. That would give me a 0 in the denominator, which is not allowed. And this is asking for strict inequality, so it can't equal 0, so the numerator can't be 0 either. They're both negative when I get to the left of -1. That's from -infinity up to -1. This is where we have that value being strictly positive, and that would be the domain of this function. I hope this has helped you to understand the graphs of logarithms a little bit better, and in the next video, we'll be taking a look at a different type of problem, namely more of the logarithm properties. And the final video, we'll look at solving exponential and logarithmic equations.